What I'm going to do today first with test 3, there is a situation with problem 3. I wasn't sure what was going on. The best thing I can do is piece together. I think the graders were inconsistent. I think that there was an error. Well, there was an error in the solution key. The grader proceeded to grade a third of it incorrectly, recovered from his mistake, and then started grading weirdly. Like people with obviously wrong answers were getting full credit. What I'm gonna do is I'm gonna work through test 3, problem 3 to begin with. In this situation, it's a standard double slit experiment in a tank of liquid rebellion. The constructive numbers are d sine theta m plus 1/2 lambda over n. The destructive, or actually, I know, I can't even get it out of the gate without messing this up. Destructive, constructive, d sine theta m lambda over n. This, you say sine theta is tan theta is little l over big L, and we get d little l over big L is m plus 1/2 lambda over n dl over big L m lambda over n. Now, what this thing ends up being is m dark ends up becoming ndl over lambda big L minus 1/2, and m bright becomes ndl over lambda L with no 1/2. And what I did is I plugged in and solved for m bright. N in this case is 1.2. Little d is 0.1 times 10 to the negative 3. The L is 0.07. Everything needs to be converted to meters. Lambda, this is the 880 version. And then big L, which is 1.2. So when to do this, to get this done, and put in the wrong number, 0.1. Yeah, it's the 880 version, and I get 7.95. You round down, so that's 7. M dark is 7.95 minus 0.5, so it's 7.45, or 7. The number of bright bands is 2mb plus 1, so 7 times 2 plus 1 is 15. The number of dark bands is m dark plus 1 times 2, or 16 bands. So 16 plus 15 is 31. What's going to happen is I will release solutions to the, now really the only, I'd have to repeat this 2 more times to get the 840 and the 800. I'll release that and put it up on Blackboard. Now, I had a difficult choice to make. I either was going to take, for a brief couple of hours, I was going to go through with it. I was going to hold on to all the tests, pick up all the tests that have already been handed out, and regrade problem 3. It's too close to finals. It's too late. So if you got a really good score and your number of bands was like 200,000, you're welcome. Christmas came early. Don't bring that test to me. If you got off with, like, you got a 31, they took points off, and you want them back, what I want you to do is take a photo of this piece of paper, because I'm worried if I have 50 people coming into my office getting a correction, it's going to kill my day and it's going to kill the rest of the week. Put your ID on that solution so I know who you are, take a photo of it and send it to me. And then I promise you, I will get it graded and I will fix it. There's a part of me that thinks there are not that many corrections that need to be made, because there were a lot of 99s. The average, in my opinion, I have not done the statistics. I would love to have done the statistics, but I need a functional computer, and computers like their power, and I was unable to do that. So what I'm going to try to do is figure out what's going on with the average. I think it's high. I think it's the least of the 3 that will get a curve. However, with those corrections wandering around and the bonus from the red out, the average is going to go even higher. If you think you really want a full evaluation of your test and you bring it to me, I'm going to regrade the whole thing. So if you did excellent on the 3rd problem and you got it wrong, you're going to have to take your chances if you want the others graded correctly. It's just that, consider the fact that you did well on that last problem compensating for other problems that may have occurred on the test. I apologize for getting this wrong. It's the graders. Some graders don't do what I tell them to do. This time they did what I tell them to do, but the answer key was off. The other problems I thought were graded correctly. Yes. The index of refraction did affect the lambda. When you dunk that double slit experiment, the medium that the light passes through is no longer air with an index of refraction of 1. It is now liquid rebellium with an index of refraction of 1.2. So that has to be taken into consideration. I did do it out there, but there was a 1.2 in the denominator. They canceled. So it reduced the amounts of calculations that I had to do. Yes? Hold on, I can't. I appreciate cold air, but it affects my ability to hear. Yeah. No, I've got it. There are 3 students who came to me. I wrote them down on a sheet of paper. They're in the yeah. No, because L is in there as well. It cancels the number of 1.2 as an index cancels with the value of 1.2 as a length. If you don't have the index of refraction in there, that L was never canceled with an effect to this wall. Yes. that is not a G, that is a non. And this is the greater. All right. Ugh. Now what I'm going to do is, so much work to be done. Problem 2, there was this little bit, R goes to A, critical angle 43.05. According to Snell's law, n sine theta is 1 times 1. Index of refraction of air is 1. Sine of 90 degrees is 1. So n is 1 over sine theta, or 1 over sine of 43.05. Some of you, when you did this, you wrote it as this and put that in your calculator, but that doesn't give you the answer. That's a different type of function.
Is this the same version?
This is the same version. I didn't bring all versions. So 1.46. Now the intent of, and this is the one that has the wonderful little accident. With this, the happy little accident was the index of refraction of the middle material is actually a step up, but a step down from the glass. So in this particular case, the 880 version was an even phase shift, not an odd. In 800 and 840, those indexes of refraction were like 1.6, 1.7. So you had an odd problem. In this particular case, for constructive, 2t is equal to m lambda. For other versions, and actually lambda over n, for other versions, it's 2t equals m plus 1/2 lambda over n. So for the 800 and 840 versions, you use this. For the 880 version, you use this. So what ends up happening is you set 2t equals 2t, the thicknesses are the same. m1 lambda 1 over n is equal to m2 lambda 2 over n. The n's cancel. The n's will actually cancel in both versions. So m1 is equal to m2 lambda 2 over lambda 1. Now you've got these lambdas. If you remember from the equation, lambda f is equal to c. So lambda 1 is equal to c over f1. Lambda 2 is equal to c over f2. So what happens is you get m2 f1 over f2. Because what happens here is you get m2 lambda 2 c over f2, and then c over f1. Those cancel, that pops up, that goes down, and you end up with this. So it's m2 800 over 1440. The fact that they're gigahertz, they're both gigahertz, so I just use the same thing. And when you take 80 divided by 144, you get M2 5/9. M1 is equal to M2 times 5/9. The only way that you can get this to work out is if M2 is equal to 9 and M1 is equal to 5. Basically, the happy little accident made the problem easier. To use the wavelength, the 800 and the 840 versions, you had to go through the steps. And I think it was 2 and 4, I think were the answers for both. Now that you've got these M's, 2T equals M lambda 1 over N, T equals M1, lambda 1 over N. This is M1 C over N F1. M1 in this case is 5, 3 times 10 to the 8th. N is 1.46, and then F1, 800 times 10 to the 9th. Once again, I cannot hear you because of the air conditioning. I will be with you in a moment. There's a 2 in the denominator. Yeah. 2, 2, 2. And I get 642 micrometers. Is the answer that I get for this. All right, and so that's problem 2. Now you would do the same procedure once you got the M1 and M2 for the other versions and plug those in. For problem 1, test 3, it was a mirror, concave mirror, which means the focal length is greater than 0. 4 diopters becomes 1/4 of a meter, which becomes 25 centimeters. The object distance is 15. The image distance is 1 over F minus 1 over O inverted. 1 over 25 minus 1 over 15. That will give you negative 37.5. Because the image distance is negative, it is virtual. Because we're dealing with a virtual image on a mirror, the image is to the right. Magnification is negative I over O. So this is negative of a negative 37.5 over image distance, which is 15. Which means this is positive 2.5. Positive implies that it's upright. Magnitude greater than 1 means that it is enlarged. We won't bother with the ray diagram. A lot of you got mixed up by the fact that it is a concave mirror and it always produces a real image. This is not true. The numbers say negative. With a diverging mirror and a concave lens, you will always get virtual images. They won't, because they're just dispersing stuff. Given certain circumstances, even the converging lenses and mirrors will produce virtual images. It is not always the case. Huh? This is the 880 version, as I've said for the fourth time. I'm going through, if I went through every version right now, we'd run out of time. I'm trying to hit the big marks before hitting the little marks. I've got the solution key in my office. I'll put that up later. Yes? No, I would say so, yeah, probably. Because virtual images are always negative, and the object distance is always positive. So you're always taking a negative of a negative dividing by a positive. That will always produce a positive. So yes. Yes. I will put the answer keys to that. That is. I have 20, like, you must read this email right now. And I'm like, well, when you get 20, I can't be with that much. The polarization is trivial. It's an unpolarized going through two filters and the filters are at an angle. So I1, I0 over 2, I2 is I1 cosine squared theta. So I2 now I said I2 is equal to 0.2 I0. So I2 over I0 is 0.2. So I2 over I0 so whatever that is for this version. Okay. And what I'll do is I will put up the, I mean, if you want to just sit here, this is being recorded. This is the answer key. I'll put up more later. It's probably not showing that well up on the whiteboard. But I will definitely show you the scantrons that I used as the answer key. So, but that's problem 3, or that's test 3. I have test 2 with me. I don't have test 1. It's currently sitting in the printer. For test 2, this is probably, I would say it's the 20 volt version, or it's whatever, did I use V2 as the version? V1 is 20, V2 is 18. So this is whatever that version is. Now the right-hand rule everybody got, so we won't go through that. Right-hand rule will not be on the final, but it will be used in the final. As in, we won't have the right-hand rule game, but those things will be used. Yes? Oh yeah, I'm gonna say that. Well, I'll go over it here. So in Kirchhoff's law, we have a circuit. I'm only interested in the current flowing through the middle resistor. So what we have to do is we have to find the J's. Loop 1, minus J1 R1 minus V1 minus J1 R2 plus J2 R2 is equal to 0. I'm going to plug in my values. Minus 5 J1 minus 20 minus 30 J1 plus 30 J2. Common factor of 5. Minus J1 minus 4 minus 6 plus 6. And that's the setup of the first equation. Oh, we got this. Minus 7 J1 minus 4 plus 6 J2 equals 0. That's for loop 1. Loop 2, minus J2 R2 plus J1 R2 minus V2 minus J2 R3 equals 0. Plug in values. Minus 30 J2 plus 30 J1 minus 18 minus 18 J2. The common number is 6 minus 5 J2 plus 6, or I'm sorry, 5 J1 minus 3 J2. Those add up, minus 8 J2 plus 5 J1 minus 3. So those are the core equations. I'm going to substitute, I could substitute any of them. Let's do J1 from here. Minus 4 plus 6 J2 equals 7 J1. So J1 is equal to 6 J2 minus 4 divided by 7. That goes in here, minus 8 J2 plus 5, 6 J2 minus 4 over 7 minus 3. Multiply everything out, minus 8 J2 plus 5/7 6 J2 minus 20 over 7. Negative 4 times 5 is negative 20 divided by 7 minus 3 is equal to 0. Multiply everything by 7. 56 J2 plus 30 J2 minus 20 minus 21. Negative 56 plus 30 minus 26 J2 equals 41. J2 equals negative 41 over 26. I'm going to keep that there for the moment. This means this is 6 negative 41 over 26 minus 4 divided by 7. This gives you minus 1.92. This gives you minus 1.58. So J1 is negative, so I1 is counterclockwise with the magnitude of 1.92. J2 is also negative, so I2 is also counterclockwise. I1 is the bigger one with 1.92. 1.92 minus 1.58 is 0.34 amps bottom to top. Excuse me. And so that is the Kirchhoff law problem. What? Okay. The bar problem, it will be on the final. I came up with a problem. I'm going to share it with you. You're gonna get as an appetizer the circle with the changing B field. The problem will be the moving bar. In this particular case, you've got a moving bar, so magnetic flux, which is BA, and d phi B dt is B dA dt. Because area is changing, this is B L dx dt, which gives you BLV. So the electromotive force is BLV. The current, which is electromotive force over resistance, is BLV over R. So this is 2 times 2 times 6.25 divided by 12. So the current is fairly significant, but I'm not interested in that. .083 repeating. The force on the bar is ILB. I is BLV over R. This is LB. So this becomes B squared L squared V over R. Or 2 squared 6.25 divided by 12. So the force is 8.33 newtons. And so that's the force on the bar. Now everything is based now on what's the direction of the current, what is the magnetic force. Here is just a general sketch. The magnetic field is out. Magnetic field is out, magnetic flux is out. The bar is moving to the right. The area is increasing. The amount of flux getting through this window is increasing in the outward direction. So the d phi b dt is out. Lenz's law demands that the induced current produced will produce a flux that opposes this. To get this done, you have to have a clockwise current. In the bar, the magnetic force as a vector, you can just think of the current direction crossed with the magnetic field. I is this way, B is out. So the magnetic force has to be this, which means that the external force has to be that way. So everything is now labeled. The external force, we've basically proven it through observation that the external force will always be in the direction of velocity.
On the final, are we using the right-hand rule or the
What?
On the final, are we using the right-hand rule or the left rule?
For the magnetic force on the bar, you use right-hand rule. To determine the direction of the current through this, you use the wrap rule. All right, last problem, test 2. B field addition. So we have 2 wires. I give you the distance. I give you the current going to the right of I1, 0.2 amps. I tell you that at this distance, the B field at that point is equal to 0. What I need to know is, in what direction is I2 and what's the magnitude of I2? How do we fix this? So I1, using wrap rule, produces a magnetic flux that is out of the board here. In order for that B field to be 0 there, the magnetic flux from this red line must be into the page. The only way that this is achieved, if we use our wrap rule, is for the current to go left. So that's the direction of the current. For part 1, the B field total is equal to 0, which is plus mu naught I1 over 2 pi R1 minus mu naught I2 over 2 pi R2. So mu naught I2 over 2 pi R2 is equal to mu naught I1 over 2 pi R1. 2 pi's cancel, mu naughts cancel, so I'm left with I2 equals I1 R2 over R1. I1 is 0.2. R2 is that distance plus that distance, 1.2. And R1 is 0.2. So I2 is 1.2. And that's the magnitude of the current. The last part is I want to know what is the B field at the midpoint and in what direction. The upper wire produces the magnetic flux that is into the page. The red wire produces magnetic flux that is into the page as well. Use right hand rule or wrap rule. For this, the B total is mu naught I1 or minus mu naught I1 over 2 pi R1 minus mu naught I2 over 2 pi R2. This becomes minus mu naught over 2 pi I1 over R1 plus I2 over R2. Mu naught minus 4 pi times 10 to the negative 7 over 2 pi. I1 is 0.2, I2 1.2. They're both at the midpoint, so the radiuses or radii are 0.5. And I get 5.6 times 10 to the negative 7 Tesla. And so that is part 2. Or that's all of test 2. Excuse me? Yes. Negative, or you could say 5.6 times 10 to the negative 7 in. Either one would be acceptable. You had this version? Yeah. I'm not. Oh, I used 0.2. That's why. All right, you did it right. I just picked the wrong number at this. Okay, we did the bar. That's a good question. Yeah, and for the people at home, the thing that I did wrong, well actually, I did it right as written, but it didn't match the test. The test version used 0.1 as the distance, and so that number would propagate through. But the procedure is correct. There's nothing wrong with the procedure, I just used a bad number from the start. All right, so we have a request. This will be the last, probably the last thing we do before we break. As a reminder, tomorrow 1 o'clock, we're gonna do, and actually before I do this, I'll just say a couple of things. Tutorial tomorrow, 1 o'clock. I'll talk about anything. I'll go over tests, finals, whatever. If you had, one of the big differences, hold on, let's take a breath. One of the big differences that I have with this semester versus previous semesters is, it used to be, I would give my finals on a Friday, and then grades are due on Monday. That sucks. I always envy Dr. Labuda because she had her final on the first day, and so she had an entire week to get her stuff straight. We almost have something that good. Our finals on Tuesday. It gives me 4 work days to get stuff done. If you have a problem with something being graded on the first 3 tests, if you have a homework score that you go, it says 5 on the problem set, but 0 on Blackboard, this is what you do. Don't come to me. I got to deal with a lot of stuff right now. People are panicking. If you're confident, hey, I'm going to get these points, take a photo of it, put your student ID on it, write a note in the photo, like this is why I think I deserve the points, or in the email, send it to me. I promise I will put it in a separate folder, and before I commit grades, I will go through the entire folder. So if you honestly think you got it wrong, take a picture, or you got it right but it was marked wrong, take a picture of it, send it in. If it was marked correctly and you definitely got it wrong, Merry Christmas, don't send it to me and don't bother me. I'm going to work for the next 6 days after that final exclusively for you and 213. I want to make it work. Yes. Tutorial will be held here, 1:30 to 1 to 2:30. Oh no, I take it back. It will still be here. Let me write it down. It will be here 2:30 to 4. 213 has 1 to 2:30. The advantage that we have is I really don't think there's someone coming into the room at 4, so I think we have the ability to go late. Now granted, that will be after 3 hours of me tutoring, so I'm going to be babbling senselessly. You may be able to get something out of me at around 4. But after that, then I'm just going to go home and pass out. That circle problem the initial position of the B can only be one of 2 directions, in or out. That's it. Yeah, this will be like the appetizer. But what I'm going to do is I'm going to set up all 4 versions. Now, for something like this, you will either have a B field that is increasing like this, or the B field with time will go like that. One where it doesn't flip sign, the other one where it does flip sign. For this, the B field will either increase in magnitude or it will flip. So will it flip or won't it flip? All I want to do is draw a perfect circle all the time. I wish I had that superpower. The B field is out, so the magnetic flux is out. Here the B field is in, so the magnetic flux is in. Now in these 2 cases, with time, the flux itself will flip. But we're not interested, Faraday's law is not interested in when does the flip happen, or if it does or if it doesn't. All it cares about is the change in magnetic field and the change in flux for that magnetic field. Here it's increasing. Here it's increasing in. Here it's increasing out. Hold on. Say your question. Well, I could give you all sorts of things. And let me finish this and then I'll address your question. Here, it's decreasing. Here, it's going to increase and come out of the page eventually. The d phi b dt always matches the dB dt. And so we got that. Lenz's law does not care about the magnetic field. Lenz's law cares only about the change in magnetic flux. The induced flux will always oppose this d phi b dt. So the induced flux is always opposite. Now, anything to produce a flux coming out of the page, the induced has to go counterclockwise. To get the flux to go in, it has to go clockwise. And so that is the setup. The equations that we use, electromotive force is d phi b dt, and that is equal to area dB dt. So the current is electromotive force over resistance, and so this becomes A over R dB dt. Hold on. Now that I've got everything up on the board, I will now go out into the crowd and talk. Well, yeah, what happens is, what we're really interested in, there are four, I've set up four potential now granted, I've got two going out, two going in, and two of those four are going to flip their beat. That's not important. What is important is the change in B. The change in B on the upper left and lower right, the change in B is out of the page. Upper left is going to go 1, 2, 3, 4, up. The lower right is going -3, -2, -1, 0, 1, 2. The way that these two are similar is the closer changes in field go up. Lower left and upper right, both the changes in field are going down. So really, it's lower left and upper right that are similar, upper left and lower right that are similar, with the case of electromotive force. 1 and 4, upper left, lower right, the B fields are going up and increasing upward. That means the change in flux is upward. means the induced is both going down, which means that both have a clockwise induced current. In lower left and upper right, the changes of E fields are down, which means the change in flux is down, which means the induced is up, and you get an induced current that's counterclockwise. The B field, the flux will always go with it. The one thing that is, okay, fine, I'll write it down, is that with time, it will later go out. And with time, this will eventually go in. But that's not what the wire cares about. The wire cares about the change in magnetic flux, which is dependent upon the change in B field. Lower left and upper right, the change is going in. Upper left and lower right, the change is going up. And so those are the four similarities. The fact that the B field, it doesn't matter that the B field starts at 1, 3, 10,000, -5, negative cubic root of pi. It doesn't matter. What does matter is its change. The thing that I do use is, as a sample problem, I would say, let's say we use the lower right. Your initial B is -1. Your current is going clockwise. How long would it take to go to -2 or 2? Which one is possible and which one isn't? In this particular case of the lower right, it will hit 2 first. It will never hit -2. Because the B field is increasing out of the table. So, the numbers on the side, I'm just using it as a reference to let you know how is the B field behaving. It's not, there's nothing, the only thing that you can get from it that's meaningful for this problem here is the direction of the change in the direction. Yeah. So eventually the one on the lower left, the B field is going to go from out to in. The one on the lower right, the B field is going to go, or I'm sorry, yeah, the one on the lower right is going to go from in to out. With time. The fact that it changes sign doesn't matter. All what does matter is the change in B field. It doesn't matter. What does matter is it changing in or is it changing out? That's it. Now, there are those types of problems that we've dealt with them where I go, given that the current magnetic field is a +2 out, will it reach -3 or will it reach 5? How long will it take? And for stuff like that, you use a simple one-dimensional, effectively a one-dimensional motion equation. Or a linear line. All right. Tutorial tomorrow, 1 o'clock. To answer the 50,000 questions that I will get, yes, this will go on the internet. Yes, the tutorial will go on the internet. I will get it done. Thank you.